everyone, and welcome back for another deep dive. Today we're going to be looking at something that's, well, kind of all around us all the time, thermal expansion. We've got some excerpts from a physics textbook to help us along. I think you might be surprised by just how much this concept really impacts our world. I mean, from like huge engineering projects to just everyday things you can do around the house.
Yeah, it's true. Thermal expansion is, well, it's everywhere. Basically, it's just matter changing its volume when the temperature changes. So, when things heat up, they tend to expand.
So why does that happen? Like, what's going on with the molecules and all that?
Okay, so when you add heat energy to something, you're basically increasing how much the molecules are moving around. They get more kinetic energy, right? And so because they're zipping around more, they need more space.
So it's like if you had a room full of people and they were just kind of standing around, they wouldn't need as much space as if they were like dancing. Right.
Yeah, exactly. More energy, more movement, more space.
Yeah.
And that's what causes the material to expand. And this isn't just solids, by the way. It happens in liquids and gases too. Although, the amount they expand can be different depending on what state they're in.
So does everything expand when it gets hotter? Are there any exceptions?
That's a great question. Well, most things do, but there are a few exceptions. And water is probably the most famous example. Between 0 and 4 degrees Celsius, water actually, it shrinks as it cools down. It does the opposite of expanding, unlike most other things. And that's because of the way water molecules interact. It's pretty unique.
Wow, that is fascinating. Water is so weird. But let's get back to those materials that, do expand when they're heated. It seems like it'd be important to know exactly how much a material is going to expand, especially if you're building something that has to work in different temperatures. How do we even measure that?
You're absolutely right. The amount of material expands. That's really important for lots of things, especially in engineering. And we measure it using something called the coefficient of thermal expansion. And this coefficient, it's different for different materials. So like metals usually have higher coefficients of expansion than, say, glass, which means they'll expand more if you heat them up the same amount.
So if you know the coefficient, you can basically predict how much something will expand or contract. I guess that would be super important for things like bridges and buildings and stuff, right?
Absolutely. Think about a bridge on a hot day. The metal, like the steel beams and all that, that's going to expand as the temperature goes up.
Yeah.
And if the engineers didn't take that into account, the bridge could buckle. That's why bridges have those gaps in them, the expansion joints. So the bridge has room to, kind of breathe as the temperature changes.
I always wondered about those gaps. It makes so much sense. And what about railroad tracks?
Same idea. Railroad tracks have to deal with big temperature swings too, right? So they have gaps between the sections of rail. Otherwise, they could buckle too. It's all about making sure those structures stay stable and safe.
Man, this is making me look at the world in a whole new way. It's amazing how this stuff is just working all around us.
Yeah.
But you mentioned earlier that thermal expansion doesn't just happen in solids, right? It also applies to liquids and gases.
Right. Think about a mercury thermometer. The mercury inside, that expands when it heats up and contracts when it cools down. So that's how it, goes up and down and tells you the temperature.
Oh, yeah. That's a classic example. It really shows how we can use thermal expansion for practical things. What about, what are some other ways we use it in everyday life?
Yeah. Have you ever, had one of those jars that's just totally stuck? You can try running the lid under hot water for a bit. And because the heat makes the metal expand a little, it loosens up the lid and makes it way easier to open.
That's a great tip. I'm starting to see thermal expansion everywhere now. It's like a hidden force, It's shaping everything around us.
Exactly. But when it comes to liquids, things aren't always simple. Things like pressure can also affect how much they expand.
Oh, so it's not just temperature. The environment around it matters too. What about the different ways things can expand? You mentioned something earlier about linear and superficial and cubical expansion.
Right. So think about a metal rod. When you heat it up, it mainly just gets longer, right? That's called linear expansion. But if you've got a flat sheet of metal, well, that's going to expand in length and width, so its surface area increases. That's superficial expansion.
So it's like the sheet is stretching out, in two directions.
Exactly.
Yeah.
And then if you've got a solid cube, well, that expands in all 3 dimensions, length, width, and height. So the whole volume increases. That's what we call cubical expansion.
So linear is 1 dimension, superficial is 2, and cubical is 3.
Got it. Yeah, exactly. And all those different types of expansion, they're important for designing things that are going to be exposed to temperature changes. Like When an engineer designs a bridge, they have to think about how much the beams will expand in length and also how much the deck will expand in area.
This is starting to make a lot more sense. I feel like we're just getting started with this whole thermal expansion thing.
So we were talking about how different materials expand at different rates, but I think you'll find this next topic even more interesting. Thermal stress.
Okay, stress already sounds kind of bad. What does that have to do with thermal expansion?
Well, imagine that you have a material that's trying to expand because it's getting heated, right? But something is preventing it from expanding. That creates a lot of force inside the material. And that's what we call thermal stress.
So like if you had a metal rod and you held it at both ends and then heated it up, it wants to get longer, but it can't.
Exactly. And that stress, it can actually be really strong. Strong enough to, bend the material or even break it if it's more than the material can handle. That's why those gaps in bridges and railroad tracks are so important. They give the material room to expand so it doesn't buckle.
Right. So engineers have to think about that when they're designing things. Are there other ways to deal with thermal stress besides just like putting gaps in things?
Yeah, for sure. One way is to choose materials that have, the right coefficient of expansion for what you're building. Like if you have parts that need to fit together really tightly, you'd want to use materials that expand at similar rates.
So it's all about picking the right material for the job. What else?
Well, sometimes you can design things with expansion joints. Those are just, like deliberate breaks or gaps that allow for movement. You see them a lot in concrete sidewalks and roadways.
Oh, yeah. Those things. I trip over those all the time. I guess they're there for a reason, though.
They are. And it's not just big structures either. Thermal stress is also a big deal when you're designing electronics. All those tiny little parts inside your phone or your computer, they heat up when they're working. And that can cause stress too.
I never thought about that. But it makes sense. All that processing power must generate a lot of heat.
It does. And engineers have to figure out how to manage that heat.
Hmm.
They use things like heat sinks and fans to make sure the components don't get too hot and get damaged.
It's crazy how engineers have to think about all this microscopic stuff.
Yeah, it's a real challenge, especially as technology gets more and more advanced and everything gets smaller and more powerful.
Speaking of small and powerful, what about that bimetallic strip we were talking about before? You said it's a really cool example of how we can, like, use thermal expansion for something useful.
Right, a bimetallic strip, it's just two different metals stuck together,
Mm-hmm.
right? And when you heat it up, it bends because one of the metals expands more than the other.
So it's like a tiny little temperature-sensitive bending machine. But how do you actually use that for something?
Well, think about a thermostat. Lots of thermostats use a bimetallic strip. When the temperature changes, the strip bends, and that can open or close an electrical circuit. So it can turn the heater or the AC on or off.
So that tiny little strip is basically controlling the temperature in my house, just because of, thermal expansion.
Pretty much. And it's not just thermostats. They use bimetallic strips in all kinds of things, like fire alarms
Mm.
or sprinkler systems. It's a really simple idea, but it can be used for a lot of different things.
It's amazing how such a small thing can have such a big impact.
Yeah, it really is. It shows you how you can use basic science to solve all sorts of problems.
Yeah.
And it's not just, in things that we build either. Thermal expansion is also important in nature.
Oh, really? Like what?
Well, think about rocks in the desert. They get really hot during the day and then cool down at night. That cycle of heating and cooling, it causes them to expand and contract, and over time, it can make them crack and break down. And that's actually how sand and soil are formed.
So even the landscape is shaped by thermal expansion. That's wild.
Yeah, exactly. It just goes to show you that these basic scientific principles are at work everywhere. We might not always notice them, but they're shaping the world around us.
This whole deep dive has been really eye-opening. Before we finish up, I'm curious to know more about how we actually measure thermal expansion, especially in liquids. You mentioned something called the balanced column method.
Right. The balanced column method is, it's a way to measure the absolute expansivity of a liquid. It tells you how much a liquid's volume will change for each degree Celsius that the temperature changes.
Okay, and how does that work?
Imagine you have a U-shaped tube, right?
Okay.
And it's filled with the liquid you want to study. And then you heat up one side of the U-tube while the other side stays cool.
So you're creating a temperature difference. Then what?
Well, the liquid on the hot side is going to expand, right? So it will rise higher in the tube than the liquid on the cool side. And by measuring how much higher it rises, you can figure out the liquid's expansivity.
It's like a tiny little seesaw, but with liquid, and the heat is like pushing one side up. But wait, what about the tube itself? Doesn't the glass expand too?
You got it. You're thinking like a scientist. You're absolutely right. The expansion you see isn't just from the liquid, it's also from the glass. What you measure is called the apparent expansion.
Ah, so it's like you're watching a dance, but both the dancers and the stage are moving, and you have to figure out how much of the movement is from the dancers.
Perfect analogy. And that's where the coefficient of real expansion comes in.
Yeah.
That's the actual change in the liquid's volume without the container's expansion.
Mm.
And you calculate that by taking the expansion of the glass into account.
So it's like subtracting the stage movement to get the dancer movement. I like that.
Yeah. And there's actually a formula for that. It tells you that the apparent expansion is equal to the real expansion plus the expansion of the container.
So it's a way to separate out the different expansions mathematically. Makes sense.
It just shows that even something that seems simple can actually be pretty complicated. But if you measure things carefully and do the math, you can really understand how things work.
This is like a detective story for thermal expansion. We're using formulas and all these cool techniques to figure out all these secrets. We've covered a lot of ground, but I want to learn more about those rule breakers, like water, and I want to know more about how we measure thermal expansion in solids, too. Okay, so before the break, we were talking about how to measure thermal expansion in liquids. And it got me thinking about water again, how it's kind of a rule breaker.
Right. It definitely does its own thing. We know that most things expand when you heat them up, but water actually shrinks between 0 and 4 degrees Celsius. That's what we call anomalous expansion. And it's a pretty big deal for, well, life on Earth.
Yeah, because ice floats, right. If it didn't, I mean, think about what happened to lakes and ponds in the winter. But is water the only thing that does that? Are there other substances that kind of break the rules?
Well, water is definitely the most famous one, but there are a few others, like antimony and bismuth. They also have this anomalous expansion thing going on, but only within certain temperatures.
So they have their own little club. What makes them so different? Why don't they expand like, normal stuff?
It's all about how their molecules are arranged and how they interact with each other, especially at certain temperatures. For water, it's the hydrogen bonds that are really important. When water gets colder, closer to 4 degrees Celsius, those bonds kind of rearrange and they make this open structure, like a cage almost. And that structure actually takes up more space than when the molecules are all jumbled up at higher temperatures, so the density goes down.
So it's like the water molecules are doing the little dance, and when it gets colder, they spread out more.
Exactly. And this weird behavior, it doesn't just make ice float. It can also affect things like, have you ever noticed potholes in the winter?
Oh yeah, they're everywhere after it freezes.
Well, some of that is because of water expanding when it freezes.
Mhm.
When water gets into cracks in the pavement and then freezes, it pushes on the pavement really hard and can make it crack even more. And that's how you get potholes.
Wow, so something so small like how water molecules are arranged can actually have a huge impact on like our roads and stuff. I never thought about it that way. So we talked about how to measure thermal expansion in liquids. What about solids? You mentioned something called Pullinger's apparatus.
Right. Pullinger's apparatus is it's a classic way to figure out how much a solid material will expand in length.
Hmm.
Basically, it tells you the linear expansivity.
Mm.
And it uses a metal rod of the material you're testing, and it's heated up with steam.
So you're basically giving it a sauna.
Yeah. And the rod is fixed at one end, but the other end can move. As the steam heats up the rod, it expands. And there's a lever system that makes the expansion easier to see. And then you measure the expansion with a micrometer screw gauge.
That's pretty clever. So you're basically making those tiny expansions big enough to measure.
Exactly. And you can use that measurement along with the original length of the rod and the temperature change to calculate the linear expansivity.
It's amazing how scientists came up with these techniques to measure something so small. Are there other ways to measure thermal expansion in solids?
Yeah, definitely. There's another method that uses optical interferometers. They use light waves to measure really, really tiny changes in length.
Wow, so there are all kinds of tools to measure thermal expansion, from like mechanical things to like fancy light beams.
Yeah. And all those measurements, they're not just for scientists. They're super important for engineers, too. When they're designing things like bridges and buildings, or even spacecraft and computers, they need to know how materials will change when the temperature changes.
This has been a really cool deep dive. We started with those tiny molecules moving around, and we ended up talking about bridges and spaceships and computers. It's all connected.
It really is. Thermal expansion is everywhere, shaping our world in so many ways.
Absolutely. Well, thanks for joining us on this deep dive into the world of thermal expansion. We hope you learned something new, and we'll see you next time.